Good evening. Are you able to hear me?
Yes, ma'am.
Okay. So I think in the last session, the other instructor have already discussed the questions on topics from week 11 and week 12. So I will be just covering the topics right from week 1 to week 10 today mostly, so that the remaining one more session, or do you have two more or one more? That will be the discussion on the mock paper on Saturday. Okay. So I have with me some collection of questions covering topics from various weeks, so that we can do it today as part of revision. So I will just share my screen. So you have this Vs of t applied across the inductor of value 0.05 Henry as shown. So a time varying current would be set up in the circuit. The expression for the Vs of t is given, and you are asked to write the expression for the inductor current in the time domain. Are you trying it out?
Yes, ma'am. 2000 into 1 minus e to the power minus 0.05.
I'm not able to hear you. Ananya?
Then
Right now, fine. Tell me, what is I of t?
2000 bracket 1 minus e to the power minus 0.05 t.
How? Let's do it here. So from the given expression for Vs, we know that omega is 1000. So L value is 0.05 Henry. So we can calculate the reactance. So now I vector it would be V divided by Z. So that will be uh, 10 by root 2 angle 0 divided by 50. J is 50 angle 90. Then this will be giving you the uh, RMS value. Then in the time domain, what you need is the peak value. So I of t, if you take it from this to the time domain, it would be 0.2 sine 1000 t minus 90 degree, because here you get when you divide it 5 angle minus 90 degree. So that would be 0.2 cos 1000 t. Okay.
Okay, ma'am.
What is the current supplied by the source? What's the answer?
10.
Okay, so it is the vector sum of these two, correct? So current supplied by the source will be so in a series AC circuit, the expression time domain expression for the applied voltage and the current flowing in the circuit are given. From these expressions, you should find out what are the circuit elements, like is it resistor, inductor, capacitor, what is the combination, and their values as well. First of all, is it the voltage leading or the current leading?
Don't know.
Which one? From the given expressions, is it the voltage or the current leading?
Voltage.
Voltage. So then we can make out that the circuit will contain,
Inductor.
yeah, inductor and in combination with a resistor. Then you need to find out the values.
Yes.
So it's same, not in a series circuit. It's simply voltage is leading, and also the phase difference is 90 degrees. Here it is plus 45. So if this is the reference line, this is plus 45, which is the voltage vector, and the current vector is here minus 45. So this is the I vector. So we conclude that it is an vector. Then what will be XL? XL will be P by I. So that will be 9 by root 2 by 3 by root 2. So 3 will be the magnitude of the inductive reactance, and L will be 3 by omega. So from the time domain expression, omega is 1. So L will be 3 Henry. Is it fine? If you have any doubts, please let me know. These are the basic problems. Just we are trying to do these, and through those, just trying to revise those concepts. If you have any doubts anywhere, please let me know.
Ma'am, can you give a little summary of theory?
Which one?
Theory instead of questions.
Yeah, we will do that. We will do that also. I mean, once these problems are also done, I will just go mention the important points. Okay, that also we can do before the end of the session. Now, can you just try this question? If so, in a series RLC circuit, what is being shown here is the voltmeter connected across RL, okay, that reads 20 volt RMS, and across LC it reads 9 volts, from which you need to calculate the value of the voltage across R, L, and C. So since we know that V1 is RL voltage, okay, so that will be square root of VR square plus VL square, which is 20. And VL minus VC or VC minus VL is 9 volts. We don't know because which is greater. So we have to consider either it is VL minus VC or VC minus VL is 9 volts. Uh, okay, so maybe I for this question I have to give one more data. Uh, because since we are not given with the applied voltage, we can just try out with the options of this MCQ, figure out the answer. Yeah, Ananya and Sonali, you have mentioned in the chat that you are ready to revise these week 1, week 2, etc. Yeah, that is fine. I just wanted to discuss with you right from the beginning, since you have to cover all the 12 weeks for the exam. I'm just discussing with you the collection of questions that I have, and maybe past 7 by 7:15 or 7:30, we can just go through the important concepts. I will just mention the important concepts. And one more thing, I have seen in the course G Space some questions being discussed from previous QPs or so, where you are discussing the answer. So if you want help in that, I will do it separately. I can just respond it in the G Space. And other than that, in the portal, when you see the live session schedule under that important links, all the live session links till date have been updated for your reference. Okay. I think I have to upload some live session notes from my side that I will do. So other than that, you can go through again what you have. Some of you here are again repeating the course, I think. So you have it with you. The other QPs, past QPs also with you, so that you can share it with the current batch students also. Okay, so I am just trying to discuss with you few numericals that I have come up with, after which we will just go through the important topics. So that is fine.
Ma'am, in first option, it is written 75.
75 or 25 volts, 12 volts, 16 volts, 75 or 25 volts. Second option is 16, 12, and uh, 7 or 25. So now we can just check with the first option.
Give us some time. I'm trying.
Which one?
I said I'm trying. Just give 2 minutes.
Okay. So the first option, if VR is 12 volts, then PL is 16 volts, BC is 7 or 25. You just check whether the square root of 12 square plus 16 square is it 20. 12 square is 144, 16 is 256, right? So it will come as root of 400, which is 20. So that is getting satisfied. and VL minus VC is 16 minus 7, 9. Or if it is 25, 25 minus 16 is also 9. So with the given voltmeter readings and with these options, it is matching with option A. Because we don't have any other data to figure out, so it will be just like we are trying out with the options given. So we just tried with the first option and it is getting satisfied. You can just check with the other, those may not be exactly matching with the given data. Okay. Now let me move on to week 2, where we have that network theorems. Okay, this question. Find the Thevenin equivalent across the terminals A and B. That means you need to find the Thevenin voltage and the Thevenin resistance. So for finding the Thevenin voltage, if I am considering this nodal voltage as V, so I'm not redrawing the circuit. That's why I'm just using a different color to mark that nodal voltage V. So what do I get is V by 2. That means towards this side, 1 ohm and 1 ohm in series. So V by 2
And
will
also we
be
can do this as V
3Vx
minus
plus
VX,
3.
right?
Correct? V. What, Ananya?
Then also we can write this as V minus Vx directly.
V
V by
minus Vx. Yeah, okay. And then what will be Vx? Vx will be V by 2. So when you substitute that, V by 2 will be 3 into V by 2 plus 3. So V by 2 and V by 2 gets cancelled, correct? So V will be minus 3 volts. So VTH is 3 volts. Then to find RTH, so since I have uh, dependent source, so I will go for finding the short circuit current, and then by VTH by ISC we can go for finding RTH. So here V by 2 plus V by 2 is 3Vx, because this 3 ampere is in parallel to this one. I can mark here again V. So we will have Vx will be V by 3 and V equal to 0. ISC equal to how much you are getting? 3. So RTH will be VTH by ISC, so 1 ohm. I don't know how many of you are right now trying to sincerely solve the questions.
Ma'am, I had a doubt.
Okay.
Here, the 3 ampere, you didn't take it into the nodal equation. Why?
Which one? 3 ampere.
This
Wait
3
one
amperes,
minute.
yes.
Wait a minute. Wait a minute. This announcement if negative say negative. Naman Sharma, are you asking this with regard to that one question which was put in the G space? That is your doubt? There was some discussion which I saw regarding the power absorption or delivery. Yeah, I will reply to that question, and okay, I will just I saw some 3 questions which are in discussion in that G space. I will reply there. Yeah, coming to this question. Wait a minute. Second.
Now here, how did you wrote that P is equals to 0?
She just applied V equal to 0 and check ISC.
Aniket?
Yes, ma'am.
Yeah, tell me, what is your doubt right now?
In the nodal, why aren't we taking the 3 amperes also?
This one, this 3 ampere is here in this node. Now I have applied KCL here only, correct? There 3 ampere won't come into picture, correct? This is V by 2. This is V by 2 equal to 3Vx.
Oh, okay.
KCL at this node. There 3 ampere
Okay,
won't be
okay.
coming.
Yes, ma'am. Sorry. And this VTH, how did you take the VTH?
Here VTH. Yeah,
Okay,
here
from the
first of all,
previous
this is fine.
calculation.
V by 2 is equal to this 3Vx plus 3.
Yeah,
Because
that is
3
okay.
V ampere is coming from this side and we have open circuited this. Then Vx is V by 2. That is also okay. Then I've substituted this one and we get V equal to minus 3.
Okay. So you just substituted Vx equal to V by 2 there, right?
Correct.
Okay, got it.
Maybe I will do one question on maximum power and then we can move on to the other weeks. Find the maximum power delivered to the resistor R. So if I consider here, okay, or better I will redraw the circuit. the open circuit voltage, and if I am applying KVL in this loop 1, what do I get?
minus 20, 20.
20 plus 2i, again plus 2i plus 30 is 0. So I will get 4i equal to minus 50. So I is minus 50 by 4 amps. Then loop 2 minus 30 plus 2 into 50 by 4, because it is minus 2 into this minus 50 by 4, so plus 2 into 50 by 4. Then sorry, here you have this. So minus 5 plus this open circuit voltage is equal to 0. So minus 30, what is this? 100 by 425 minus 5 plus VOC is 0. So VOC will be 10. And RTH will be
What?
RTH will be when you short circuit this voltage sources, it will be 1 kilo ohms. So maximum power will be this VTH square by 4 RTH. So that will be 100 by 4 kilo ohm. So that will be 25 milliwatts.
Okay.
So this was question number 6. So that is regarding week 1 and week 2. Again, same week 3, you would have seen these same theorems applied to the AC circuits. So that's it on week 3. Then week 4 and week 5, the Laplace. So Laplace, what you need to again revise or refresh is the skill of mainly the partial fractions. That I can just tell you in general. So partial fraction, suppose the Laplace is of the form a by s into s plus p1 into s plus p2. Then we can decompose that by partial fraction as constant, some constant c1 by s, which corresponds to this, plus another constant c2 by this s plus p1, another constant c3 by s plus p3. So these are actually distinct poles. S is 0 is a pole, P1 and P2. So there, this is the case of distinct poles. Okay, and also of first order. Here we don't have that square term or something like this. So a typical, what to say, transfer function is of this form. Then you can decompose by partial fractions like this one, and then you find out the constants. Okay, so how do? You can cross multiply, or you can take when you apply s equal to 0 in this and then find out. So whatever, you can find out c1, c2 and c3. Then another case is if this is of the form when one of the poles is repeating. Say for example, if P2 is repeating, so that I will have the term s plus P2 the whole square. Then by partial fraction, you have to decompose like C1 by S plus C2 by S plus P1 plus C3 by S plus P2 plus C4 by S plus P2 the whole square. That will be the way you will decompose using partial fraction. And if it is of the form when one of the term in the denominator is not factorizable, like S square plus BS plus C, okay, then it will be of the form C1 by S plus P1 plus C2S plus C3 by S square plus BS plus C. So this is just for your information. I've written here. Mostly, it will be the case, a simple case where you can do it within a short time. You can decompose and find out, as you would have seen even for the case of quiz. Okay. So this is how you need to decompose. Then the main thing is you have to go through all the basic Laplace transform pairs. I think that you can go through. Should I mention it right now? No, just what has been even discussed in the lecture, that elementary signal, that of sine, cosine, exponential, then impulse, all those things. Then sine with a shifted version. Then the main thing is that of initial value and the final value theorem. That means limit f of 0 minus the initial value will be limit s tending to 0, s tending to infinity, s into f of s, and the final value will be limit s tending to 0, s into f of s. So finding the initial and final value, all these things are in connection with the Laplace. Okay. Then coming to week 6 and 7, maybe I can just do some one or two diode problems. What was the question number? Question 6. Okay. Find the current I shown in the circuit if the diode is ideal with 0 forward voltage drop.
One ampere.
How much?
1 ampere.
1 ampere or 1 milliampere? It is kilo ohms.
1 milliampere.
This is where you had done mistake in the case of quiz 2 also. 400 ohms, 0.4 kilo ohms. Do you remember?
Yes, ma'am.
Ah. So don't lose your marks simply. So take care of the units. So this is not a pen and paper exam. So we don't know whether you are making mistakes just ignoring the units or other mistakes. So only for exactly the right answer we can give you marks. So these sort of mistakes you better see not to commit again. You had lost your marks even for your quiz because of this. Okay, so this one simple diode problem, correct? So what will be the potential here? That will be uh, if I mark it here VA. So what will be VA? By voltage divider rule, it will be 12 into 6 by 6 plus 6. So that will be 6 volts, and I will be 6 volts minus 3. This VA is 6, this side it is 3 volts divided by 3 kilo ohm. So that will be 1 milliamps. Find Ix if the diodes are ideal with zero forward voltage drop.
Now I forgot how to solve this type of questions.
How much?
I said I forgot to solve this type of questions.
Okay, let us solve it right now here. So I will just draw this. So here this side, it will get connected to which one? These three. Among these three, it will be
15 volts.
D3, D4 or D5.
D3.
D3. So 15 volts it will be. Okay. So D3 on, D4, D5 off. So Ix will be, if I consider here Vx, it will be Vx minus 12 by 2 kilo ohm plus Vx minus 6 by 2 kilo ohm. That means Vx minus 12 by this one. Here this side Vx minus 6 by 2 kilo ohm. That is equal to this side it will be 15 minus Vx by 3 kilo ohm. So by simplifying this, you will get 15 minus Vx equal to 3 into Vx minus 9. So how did I write this one? Which was the direction here? This side, correct? Ix. Yes. So Ix is like this. So that is Vx, this potential, minus this Vx minus 12 by 2 plus Vx minus 6 by 2, and that is equal to 15 minus Vx by this 3 kilo ohm, from which I can write the relation as 15 minus Vx is 3 into Vx minus 9. So you can solve for Vx. You will get the value to be 10.5 volts. So with 10.5 volts, D1 is between D1 and D2, which will be on and which will be off.
That 12 volt one will be off and 6 volt one will be on.
Yeah, so D1 will be off and D2 will be on. So Ix will be, with this condition of the status of the diodes D1 off and D2 on, Ix will be 15 minus 6 by 2 kilo ohm plus 3 kilo ohm. So that will be 9 by 5. So 118. So 1.8 milliamps. So these sort of questions you will not get for the exam, but we are just doing a bit more a bit something where which will help you even to do attend any sort of questions for the exam. That is even seen through the assignments as well. So if you can do sort of these questions, you will be able to do a little bit easier questions for the exam. Okay. So don't worry if you see like these multiple diodes and all. Always you go with the simpler concepts. We can do one question on clipper and clamper, and then we can move on to transistors. So these were just to check for the status of the diodes. Now with the clipping and clamping. So question 9. considering the diodes to be ideal, you need to calculate the minimum and maximum value of the output waveform. So for V in greater than 4 volts, which one will be on? Which diode?
D2 will be on.
D2 will be on. And for V in less than minus 4 volts, the diode D1 will be on. So during the positive half cycle, for V in greater than 4 volts, D1 on and D2 off, and V out will be
4 volts.
4 volts. Again, during the positive half cycle, for V in less than 4 volts, what will be the condition of the diodes?
Until -4, it will be.
Both will be off, correct?
Yes, ma'am.
Both the diodes will be off, and V out output follows the input.
V in.
So maximum value of the output will be 4 volts.
4 volts.
Then come to the negative half cycle. During negative half cycle, for V in between this -4 and 0, again both will be off and output follows input.
Yes, ma'am.
And when the V in is less than this -4 volts, we had seen D1 on and D2 off. So V out will be
That we have to.
-4 plus you have a resistor there, correct?
Yes.
10 kilo ohm into the current flowing. 10 kilo ohm into I. So I will be
Can you show this?
V in plus 4
Divide by R equivalent.
by 20 kilo ohm. So that will be -10 plus 4, because what is that -10? Because input is 10 sin omega t. So -10 plus 4 by 20 kilo ohm. So that will be minus 0.3 milliamps. So V out will be -4 plus 10 kilo ohm into I. So that will be -4 plus 10 into -0.3. So -3. So -7 volts. So that will give you the minimum value of V out. This is because when the output voltage will be minimum when input voltage is minus 10 volts. Okay, so
Yes, ma'am.
it will be like this. This is plus 10, this is minus 10, this is our input waveform. Output will be
First it will stay till 4, then minus 7.
this is plus 4, this is minus 7. So this is actually getting clipped at 4, and this will be actually, we will get till minus 7. Sorry. Okay. Now one question on this one. What to say? Clamping we can do. Then we can move on to the diode is ideal and the time constant is large enough. You need to find out the output corresponding to the given input. So you can just consider without the bias voltage. Here the bias voltage is that minus 10 volts. So without the bias voltage, it will be just the case of a positive clamper, correct? So shifts the entire entire waveform to the positive side by uh, 15 volts. So already you have plus 5 volts on the positive side. So again, and another shift by 15. So it will be without the bias voltage. You can see that the cathode is on the top. So it will be the case of a positive clamper. So it will be the case like this. How much will be this peak value? You had already plus 5 on the positive side and then another shift by 15. So what will be this value?
20.
20 volts. So this will be the case of the output waveform without that bias voltage. Now with bias voltage of minus 10 volts. What will happen?
It will shift down by 10. So our max will be at 10.
Yes. So 10 and minus 10. Correct? D is conducting during the negative half cycle. And what else we have? We have that voltage multiplier circuit. So maybe again go back to that one question. So if you try to recollect, this is the circuit of a can you identify the circuit? I just now mentioned also voltage multiplier. What is the multiplying constant here? It's the case of a voltage doubler, correct? If you can try to recollect, I don't know how many of you have right now covered this week in your preparation for the exam revision while you are doing the revision. So this is the circuit of a voltage doubler, and given input is V in is 5 sin t, and you are asked to calculate the steady state value of VC1 and VC2. So what do we get at VC1 will be the peak value of the input plus Vm. Okay, if you can try to recollect the functioning of this operation of this voltage doubler circuit, plus Vm will be across Vc1. So Vm here is 5, so 5 volts, and Vc2. So when this one, it will be charging in this way. So plus towards the bottom and minus towards the top. But since the polarity of Vc2 is given like plus at the top, so here it will result in a negative value. And what will be that? 2 Vm. So it will be minus 10 volts. And one more question on that. Vn is 5 sin t volts. Find the value of Vc3 and Vd3. So this again we had seen in the case of that higher voltage tripler or quadrupler, correct? So what do we get here is Vm. Here is 2 Vm. So when you, I told you, I had explained to you, when you take the voltage across this and this, it will be 3 Vm, and that is the case of voltage tripler. Similarly, here again, between this and this, you will get 2 Vm plus 2 Vm, 4 Vm. So right now what is being asked is Vc3. So that will be actually 2 Vm. So it will be 10 volts. And here what is being asked is Vd3. Vd3 will be what? V in minus Vm. So V in minus 5 volts.
Yes, ma'am.
So for the diode problems, you need not worry whether the diode is having a cut-in voltage of some value or is it the ideal case. That will be specified in the question mostly. If not specified, by default, you treat it as an ideal diode with 0 forward voltage drop. Okay. Then coming to the so in the week 1 and 2, you had that case of what to say, that complex power. You have that um, average power, reactive power, and apparent power. So average power is measured in watts, reactive power in volt ampere reactive, and apparent power is in volt ampere. So apparent power is the resultant of these two. So actual power in the circuit is the power consumed in the circuit, which is the average power. So Vi cos phi will be your average power, reactive power will be Vi sin phi, and apparent power will be Vi. Okay. So if you have where this cos phi is actually the power factor. So if power factor is 1, that is unity power factor, implies that cos phi is 1 or phi is 0. So phi means the phase difference between the voltage and current, which is 0 means they are in phase. That happens with a resistive circuit. So resistive circuits will have unity power factor, and pure reactive circuits will have zero power factor. That means if cos phi is 0 means phi is 90 degree. So pure reactive elements like pure, if it is a pure inductive circuit or pure capacitive circuit, will have zero power factor, and unity power factor is the case of the resistive circuit. So then what else? If it is voltage is leading the current, the circuit will be inductive, and if current leads the voltage, it will be capacitive in nature. And what is the case of series resonance? You have in RLC uh, Z is the impedance will be square root of R square plus XL minus XC the whole square. And when XL is equal to XC, that means the inductive reactance is equal to the capacitive reactance. This term becomes 0, so that impedance will be simply R. So at series resonance, the series RLC circuit will behave like a pure resistive circuit. Okay, so impedance will be minimum and current flowing will be maximum. Wait a minute. Okay, so at series resonance, impedance will be minimum and the current will be maximum. Then what else we were discussing? Uh, what else in week 1? Hope you know to, yeah, the main point that you need to take care of something if it comes. Um, if it is in the time domain, you know that say V of t is Vm sin omega t, this Vm is the peak value. Other than that, something like simply it is given in polar form some 10 angles 0 without specifying this, then by default you consider this as the RMS value. Just like the case of diode, whether it is RMS or peak, mostly it would be specified to give you the clarity. But in vector form, suppose something like this given and nothing is specified, then by default this should be treated as the RMS value. But if it is in the time domain, the things are clear. This will be peak value. Okay, so something like this in the vector form given, don't treat that 10 as a peak value unless otherwise specified. If it is specified, you go accordingly. Other than that, you treat by default RMS. This has been always been emphasized even in the corresponding live session. So I'm just reminding you on that. Okay, and we had seen in the second question of today's session, finding the total current supplied by the source. So that will be the vector sum of the that circuit. Uh, something like this. Okay, so all these vector concepts that you should know. Those things we have already covered. Then coming to, maybe we can move on to Thevenin and Norton. We have taken the case of Thevenin today, and with the help of that, we had done one question on maximum power also. So if it is in the case of complex thing, you know that for maximum power, it should be the complex conjugate, the relation for maximum power. That is the thing. Then maybe we can move on to the transistor circuits. So transistor, even in through the quiz or in the week 7 discussion, we had seen the main thing is that voltage divider biasing. So R1, R2, RC, RE. Then if you consider the common emitter amplifier circuit, you have the coupling capacitors, then here the bypass capacitors. So you should know the role of these coupling capacitors and the bypass capacitors. So the DC analysis, doing the DC analysis, and you try to find out the operating point, which is the value of VCE and IC operating point. Then AC analysis, through the AC analysis, we try to write the expression for our output. V out is minus GM RC VI. So this is your small signal voltage gain. So GM is transconductance. Which is IC by VT. VT will be approximately 25 millivolts. Then what was the expression for this GM? Different expressions that we had seen through that lecture. I mean for the MOSFET. MOSFET, again, this is V0 is minus GM. In place of RC, it is RDVI. And here GM, in terms of that device aspect ratio, that is W by L, and the drain current and all, how do you get? So MOSFET, before coming into this expression for the transconductance, what are the regions of operation here? Here in the BJT, you know that for the transistor, for the bipolar junction transistor, to function as an amplifier, it should be biased in the forward active region. Function as an amplifier. So what is forward active region? Base emitter junction is forward biased and collector base junction is reverse biased. And in the case of MOSFET, it is in the saturation region that it functions as an amplifier. And another region is the linear region or the triode region. So what is the expression for the drain current in the saturation region? What is the expression for the drain current in the saturation region?
1 by 2
1 by 2
mu COX
un COX W by L.
VGS minus VT whole square.
Now the linear region,
Half mu n COX
un COX,
W by L
yeah, then VGS minus VT into VDS minus VDS square by 2. And now what is that overdrive voltage or saturation voltage? It will be VGS minus VT. The VDS sat, I should write it as is VGS minus VT. So you can see that in this expression for the drain current in the linear region, if you substitute for VDS as VGS minus VT, you can see that this term becomes VGS minus VT into VGS minus VT. So VGS minus VT the whole square minus here also VGS minus VT the whole square by 2. So that will become half into VGS minus VT the whole square. So half mu n COX W by L VGS minus VT the whole square. That will give you the expression in the saturation region. So when the value of the drain to source voltage is equal to VGS minus VT, then the device will enter from the linear region into the saturation region. So that is the overdrive voltage or the saturation value. So this threshold voltage will decide the conduction, and these are the device parameters. W by L, the width to length of that. So aspect ratio it is called as. Mu n is the mobility of electrons. COX is the oxide capacitance per unit area. Okay, so these are the two regions of operation. So for in the linear region, when the value of VDS is very small, you can see that the second term becomes negligible, that VDS square by 2. So that you can have a linear relationship, and hence it is called as the linear region. Correct? For very small values of VDS, this VDS square by 2, when you square the smaller values, still it becomes small, so that whatever you subtract here by means of the second term, that will become negligible, and it will be almost a linear relationship. Uh, Wait a minute. Okay. Um Now coming to this one, small signal voltage gain. There, in the case of BJT, we have seen minus GMRCVI, and you know the three different configurations there. It is the common emitter configuration. So emitter is coming in common between the input and output. To the base, we feed the input. From collector, we take the output. Similarly, the other two configurations, common base and common collector. In the case of common base configuration, base terminal is coming in common between the input and output. We feed input to the emitter terminal and we take output from the collector terminal. And in the case of common collector, collector terminal is coming in common between the input and output. To the base, we feed the input. From the emitter, we take the output. And common emitter configuration is basically a inverting amplifier. Common base is non-inverting, and common collector, the specialty is unity gain. So we make use of it as a buffer for impedance matching. Okay, then MOSFET again. Accordingly, we have the common source, common gate, and common drain configurations. Then now you tell me the different expressions for GM in the case of MOSFET. let me just take it. I don't remember that final expressions. Let me just tell you. You have it in week 10, lecture 6, correct? Towards the end, that common source amplifier small signal analysis. So that will be, I can write it here, root of 2 mu n cox w by L id. Okay, then you have other expressions also. You just you can refer the end of week 10, lecture 6. Okay, so those will give you the relationship between the device parameters, the drain current, all such things. Then what else? Yeah, in week 9 we had seen that Darlington pair, correct? So maybe one question. So Darlington pair is, you have, it is called as the super transistor. You have two transistors. So this is the base terminal. This will be connected to the collector terminal of the second, and this will be the emitter terminal. So this is Q1, this is Q2, IE1, IE2, and this will be IB2, this will be IB1. So as such, what do you see? The super transistor, which is the these two, composed of these two transistors. So as such, this one enclosed inside this red, the base collector and emitter terminal coming out. So that will be the Darlington pair. So it is called as the emitter follower. Okay, so maybe one simple question on that. I think the same question you would have seen the assignment, I think, correct? If you can try to recollect. Yeah, this itself is enough for understanding this thing. So if this you can see it from the assignment, I may not spend time on this. Okay, just refer the assignment, because since you have your mock by 8:30, maybe you can just go and refresh having your dinner. So I will just try to wind up in another 5 minutes or so. Okay. Yeah, so week 11 and week 12 already I hope the other instructor had done. So what you need to do is um, just try maximum to attend it today itself in the exam mode, and then in the next session he will be discussing the mock solutions. So other than that, any question as I had seen from the G space, any question from the previous QPs or the current assignments or something, any doubts you can discuss in the G space, or you put it in the discourse, tagging both of us. So we will just see to that and respond to you. And already I mentioned to you in the G space, I had seen that one on that power delivery, which Naman Sharma was asking on. Then one another question like Vx, Vy or something like that. So I will just reply to that in the G space itself. Okay. Yeah. So basically, always mentioning even right from ESTC, the one common mistake always you people commit is with regard to the unit, and one another thing is with regard to the polarity. Okay. So when in the case of -10, if you are entering is 10, we can't even give you partial marks. So please take care of the polarity. Say for example, here in the case of that voltage multiplier circuit we had seen, suppose if the polarity of VD3, sorry, VC2 here was given like plus at the bottom and minus at the top, here it would have been plus 10 volts. Okay, so those sort of things you should be careful. And again, units, whether it is milliampere or microampere, nanoampere, then kilo ohms or ohms, please refer to the unit and then answer, because you would have done every calculations right, and finally while entering into the system, if you go wrong with in terms of units, you are losing your entire marks there. So this we had seen even for quiz. So don't do that. Please relax and do. So other than that, those who have sincerely solved all the assignments, all the QPs, etc., definitely you can score either the top grade or the at least the second top grade for this paper. Always we see that through assignments you do the most tough problems, and QPs will be comparatively easier than your assignment questions. So if you are done with assignments thoroughly, you should be able to score well for your generally the quiz or the INSEM. Okay, so any other doubts, you can put it in the discourse or put it in the G space, whatever. We will respond to that. So the portions after quiz 2 will be given little bit focus, but that doesn't mean that you have less weightage for the other things. You may have even copy from the other weeks also. So go through the entire week 12 topics. Okay, the mock paper will give you an idea on that. Okay, so anything else?
No, ma'am.
Okay, so you can refresh and then please try to attend the mock exam at 8:30. All the best. So we'll be seeing only after the exam. Okay, so maybe we will be meeting again only for the diploma course, maybe after your signals for AEs or something. Okay, so see you sometime later. Thank you all.
Thank you, ma'am.
Yeah, thank you.
Thank you, ma'am.
Yeah, do well. All the best.
Thank you, ma'am.
Thank you.